Hey everyone, today we are diving into a technique that can cut your LLM application costs in half while also making your system significantly faster. If you are building anything with large language models, whether it is a chatbot, an agentic system, or any AI-powered application, you are constantly balancing cost, latency, and accuracy. By the end of this video, you will have a clear understanding of semantic caching, why it works, and how it helps optimize all three of those dimensions. I'll also walk you through exactly how to implement it in your own projects. You'll also get access to a dashboard and an agentic chatbot where you can fine-tune semantic caching on your own data and test it directly. So with that, let's get started. Okay, so first, why do we even need this? The thing is, every single time someone asks your LLM a question or the LLM engine takes an action, you're paying for it. Like with Cloud Sonnet, you're looking at $3 to $15 per million tokens. Now, that might not sound like much, but here's what may surprise you. When you actually run the agentic applications in production, somewhere between 40 to 70% of your queries are basically the same question, just worded differently. Think about it. Someone asks, how do I get a refund? Then another person comes along and asks, I want my money back. Then someone else asks, what is your refund process? Same question, same answer. But you're hitting the API every single time and paying for every single call. And that is just the money part. LLMs are also slow. They take somewhere between 2 to 5 seconds just for the model response. And that is before you add tool calls or database queries or whatever else your system needs to do in the backend. Meanwhile, your users are sitting there expecting instant answers, especially for questions they know other people have probably already asked. So the fix is actually pretty obvious when you think about it. Cache those common answers and serve them instantly when similar questions come in. You save money, you save time, everyone is happy. We are talking about 50 to 70% cost savings while making the whole system feel much faster. Okay, so before we go too deep in the theory, let me show you something practical. About 2 years ago, I built this system called RagGPT in one of the videos. And you can see the full pipeline here. There is the data ingestion part where you prepare everything, and then there is the inference flow where someone asks a question and you retrieve context to generate an answer. Pretty standard RAG setup, right? Well, in the next few slides, I'm going to show you exactly how we can bolt semantic caching onto this thing. And the cool part is, this same approach works for pretty much any LLM application, not just RAG. But I wanted to show you a real system because that makes it way easier to visualize where the caching actually fits in. Now, you might be thinking, okay, caching, yeah, we have been doing that forever. What is special about this? And you're right to be skeptical, but traditional caching only works with exact matches. So if someone asks, how do I get a refund, and you have cached that exact string, boom, cache it. But the second someone asks, I want my money back, which is literally the same question, your traditional cache is like, nope, never heard of it, total miss. This is where semantic caching changes everything. Instead of matching character by character, it actually understands what the question means. It looks at the intent behind the words. So it knows how do I get a refund and I want my money back are asking for the same thing, even though the words are totally different. And that is huge because your cache hit rate just explodes. You're not matching strings anymore. You are matching meaning. All right, so how does this work under the hood? The secret sauce is something called embeddings. Basically, you take your text and convert it into a list of numbers, like a vector. For most open source models, that is usually 384 or 768 or 1024 numbers, while higher end models like OpenAI's can go even bigger. So when someone asks, how do I get a refund? You get something like this. And when someone else asks, I want my money back, you get a vector like this. Now, here's the magic. Similar meanings create similar vectors. These two vectors are going to be really close to each other in this high-dimensional space, even though the actual words are different. Why does this work? Because these embedding models are trained on absolutely massive amount of text, and they learn all these semantic relationships. They know refund and money back mean similar things. They get the context. Okay, so we have got these vectors. Now what? We need to measure how similar they are, like how close are they in this high-dimensional space. And for that, we use cosine distance. I'm not going to bore you with the math, but basically it gives you a number between 0 and 1. Lower number means more similar. So like 0 means queries are identical. Between 0.1 and 0.3, that's very similar, like you just rephrased it. Once you get above 0.7, totally different topics. Let me give you a real example. How do I get a refund compared to what is the refund policy might give you 0.14. That's a match, right? But how do I get a refund versus can I reset my password? That's 0.78. Totally different, no match. Now, quick caveat, these numbers can shift depending on which embedding model you're using and what your data looks like. So don't just copy these thresholds blindly. Oh, by the way, if you want to really understand how embedding models work at a deeper level, I've got this tutorial from earlier in the channel where I actually visualize all this stuff. I'll link it below. All right, now we get to the important part, the threshold. This is the number that decides whether you return a cached answer or call the LLM. Basically, you're asking how similar is similar enough. And this is where it gets strategic, because there is always a trade-off. Set a low threshold, say 0.1 to 0.2, and you're being super strict. Only extremely similar queries will match. You will have high precision though, meaning when you do get a hit, you're confident it is right. This is what you want for healthcare or legal or these type of sensitive domains where mistakes are really costly. Minimum threshold like 0.25 to 0.35 gives you a balance. This is your sweet spot for most applications. Start here. High threshold 0.4 to 0.5 is more lenient. You will get way more cache hits, but you're also going to get some false positives where the answer isn't quite right. Use this when cost savings matter more than perfect accuracy. The thing is, there is no magic number that works for everything. It completely depends on what you're building and what matters most to you. So what are the caching strategies? Let me break them down for you. First up, exact match. This is the old school caching. Lightning fast, 100% accurate when it hits, but zero recall on paraphrases. Someone changes one word and you are back to calling the LLM. Second, fuzzy matching. This is the middle ground. It uses something called Levenstein distance to handle typos and small variations. So if someone types REFUDN instead of refund, you still get a hit. It is faster than semantic caching, but it still misses paraphrases. Third, semantic caching. This is what we have been talking about. It actually understands meaning. The trade-off is it's slower because you need to compute embeddings, and it uses more memory, but that higher hit rate usually makes it totally worth it. In reality, most production systems actually layer this, like exact match first for instant hits on identical queries, then semantic caching for everything else. Best of both worlds. We also need to know how to measure whether this is actually working. And for that, there are 4 key metrics that we can track. Precision. It means of all your cache hits, how many were actually correct. You want this high because false positives means you are giving users wrong information. Recall. Of all the queries that should have hit the cache, how many actually did? Higher recall means more cost savings. F1 score. This is just the harmonic mean of precision and recall. It's a single number you can optimize when you are tuning everything. Hit rate is the percentage of queries served from the cache. For most apps, 40 to 60% is pretty normal, but it really depends on your use case. Here's the thing though, these are all connected. When you adjust your threshold, you are trading precision for recall or vice versa. It's a constant balancing act. All right, now let's see how we can actually add this to our RAG-GPT system. I have simplified the diagram here by compressing the data pipeline and the RAG pipeline into those boxes on the right. The new component is on the left. So here's how it works. User asks a question, but instead of going straight to the RAG pipeline, we first run it through an embedding model and do a vector similarity search against our Q&A cache database. Then we check the results. If we get a cache hit above our threshold, meaning the question is semantically similar to something we have answered before, we just return that cached answer immediately. If there is no hit, we fall back to the regular RAG pipeline exactly like before. And then we add that new Q&A pair to the cache for next time. The cool thing about this pattern is it is not limited to RAG. You can apply this same approach to any agentic system. You just need to think about where the caching layer fits in your architecture. Okay, here's something important that people often miss. Semantic caching can give you wrong answers. Here's why. Sometimes queries are semantically close but need different answers. For example, how do I return a product versus can I return a digital product? They seem similar, but digital products often have completely different return policies. So this is where re-ranking comes in. It's a two-stage approach. Stage 1, your semantic cache. This is optimized for recall. You grab the top 5 or so candidates that are semantically close. Stage 2, the re-ranker. This is optimized for precision. It validates whether these candidates actually answer the user's specific question. You have got 3 options here. Simple keyword matching. Super fast, like 1 millisecond, but pretty basic, just checks for keyword overlap. Cross-encoder is the middle ground, takes about 50 milliseconds, gives you a good accuracy, and you can run it yourself without API costs. And LLM validator. It has the highest accuracy. It can actually reason about whether the answer matches, but it is slow, around 500 milliseconds or more, and you are paying API costs. My recommendation, start with just semantic caching, get that dialed in first, then if you are still seeing bad answers, add a cross-encoder. That's usually the sweet spot for most production systems. All right, now let's take it one step further and see how it looks like when we add re-ranking to our RagGPT project. I've also compressed the caching part into one box so we can focus on what's new. So as you can see, user asks a question, it goes through semantic caching, but this time, instead of returning one result, we grab multiple top candidates from the similarity search. Those candidates go to the re-ranker, and it can either be a cross-encoder or an LLM, it's your choice. I've shown both here just to illustrate the options. After re-ranking, we check again. If we have got a high confidence match, we return the cached answer. Otherwise, we go back to the regular RAG pipeline. Now let me give you some real examples of where this works. First, customer support chatbots. Those 24/7 support bots are the perfect use case. Set your threshold around 0.3 to 0.35, maybe add a cross-encoder, and you will typically see 50 to 70% hit rates. That means you are cutting support tickets by more than half while giving instant responses. Second, e-commerce FAQ systems, like product questions, shippings, and returns. Go a bit lower on the threshold, maybe 0.25, add an LLM reranker if you want a better guardrail, and you are looking at 40 to 50% hit rates with high accuracy. Next, healthcare information. This is where you need to be careful because it is a critical domain. Use a conservative threshold like 0.15 to 0.20, and definitely use an LLM reranker with reasoning. Your hit rate will be lower, maybe 20 to 30%, but accuracy is way more important here. And as the final use case here, enterprise knowledge bases, such as internal docs, policies, and procedures. These often have the highest hit rates, sometimes 60 to 80%, because employees ask very similar questions about the same topics over and over. The key takeaway here is that the domain dictates the strategy. Don't just copy these numbers. Think about what matters most for your specific use case, and then adjust your system based on that. Okay, if you're actually going to deploy this in production, there are 4 big things you need to think about. First, performance at scale. You can't just throw embeddings in a Python list and loop through them. You need a proper vector database like Pinecone, VV8, Quadrant, etc. These are built for similarity search and can handle millions of entries without killing your response time. Second, updatability. Your cached answers won't stay accurate forever. Things change. You need a strategy for invalidating old entries, versioning your FAQ content, and warming the cache with updated embeddings. Build this from day one because adding it later is going to be way more difficult. Third, observability. You need to be tracking your metrics constantly. Hit rate, precision, recall, latency, and costs. Set up logging and alerts so you know immediately if something goes wrong, like if your cache performance surpasses the expected range, or if you are getting a spike in false positives. Fourth, cost analysis. Do the actual math on your ROI. Calculate your LLM API savings from cache hits. Subtract your infrastructure costs for the vector database and hosting. Factor in re-ranker costs if you are using one, and put a number on the value of faster responses. Make sure this actually makes financial sense before you go all in. And my advice, start conservative with your settings, use re-ranking in production, monitor false positives rates like a hawk, and A/B test any changes. All right, finally, we got to the fun part. I built this complete dashboard where you can test all of this with your own data. We are going to see it in action in a minute, but let me quickly walk you through it. Step 1, you upload 2 CSV files. Your FAQ entries, which is basically your cache, and your test queries with ground truth labels showing what should hit and what shouldn't. And yeah, you can either have humans label this or use LLMs to do it for you. Humans are better, obviously, but if that's too expensive or you need to move fast, LLMs work fine. Step 2, the dashboard compares all 3 strategies for you: exact match, fuzzy match, and semantic caching. You get confusion matrices, all the metrics we talked about, and everything you need to make an informed decision. Step 3, you can play with different thresholds and immediately see how precision and recall change. This is where you find that sweet spot for your specific data. Step 4, add re-ranking and compare the different methods. See exactly how much each re-ranker improves your accuracy and performance hit. And don't forget to tune the LLM system prompt. if you're using an LLM reranker. Step 5, the dashboard gives you recommendations based on your actual data and lets you export the config to use in your real application. The data format is also super simple. Just CSV files with your queries, answers, and labels. Oh, and one more thing. I also built this RAG chatbot that you can play with. You can either use the default dataset I provided or plug in your own data. It's built with LangGraph, OpenAI, and ChromaDB, and it supports semantic caching out of the box. Here's what the architecture looks like. On the left, you have got the raw LangGraph workflow for the RAG agent. On the right, same thing, but with the caching layer added. Quick overview of how the chatbot itself works. It's a RAG agent that takes your question and does a vector search over the documents. It also evaluates what it finds. If the documents aren't relevant, it rewrites the query and tries again. This keeps going until either it finds relevant stuff or it hits the maximum number of attempts. And once it gets good context, it generates an answer and returns it to you. Alright, so that was the theoretical part of the video. In the next part, I want to show you how we can implement different caching strategies, how we can add re-ranking to it, and also how we can fine-tune the strategy and find the best threshold for our dataset. This is a project that I prepared for you. I will include the link in the description of the video. It's already uploaded on my GitHub and you have access to it. So we have the documentation folder that contains the information about the project, the schemas, and we have the evaluation dashboard. This is the dashboard that I showed you in the video and we are going to test it together. We have RAG chatbot with semantic caching. This is the RAG project. Again, we are going to see it in action together. And we have the tutorial folder. So in order to run the project, you need to have access to OpenAI models. And for that, all you need to do is to create a file called .env and add your OpenAI key just like this. So with that, both projects would be able to load the API key and interact with the OpenAI models. Besides that, you also need to follow some steps to prepare the environments, install all the dependencies, and then you can execute both projects. I created a README file for you that contains all the information about the project, including what it is, what is the purpose for the dashboard, what is the purpose for our RAG chatbot alongside the schemas. And also it tells you how you can execute the projects individually. So for example, to execute the evaluation dashboard, you have to, after you have the Python environment, of course, you have to change the directory to the evaluation dashboard, install the package, and then you can easily run the app using Streamlit run command. Okay, so let's go through the tutorials and let's see how we can implement semantic caching. Here I have two notebooks. One is called Semantic Caching Basic. The other one is called Semantic Caching Comprehensive. In the first one, I just simply want to show you how we can implement semantic caching without anything else. And also, I don't want to use any external database beside what we have inside this notebook. So I simplified it in a way that you can easily follow and understand how it works. Then we have Semantic Caching Comprehensive. After we go through the basic notebook, we'll go through this one. In this one, I will show you different caching strategies. We will implement different re-ranking strategies. And it also shows you how you can fine-tune the strategy to find the threshold for your data set. And this is the data that I'm using for this tutorial. And then we are going to go through the dashboard and the RAG chatbot together. So let's begin and let's go through the first notebook. So this is a simple step-by-step guide for implementing semantic caching itself. The first step is to install and import the library. So I assume that you already have an environment, and that environment already has all the dependencies that we need. So the environment that I want to use for this project is called, let me open the environment here. So it should call, this is the one. So this is the environment that I prepared for this project, and this is the one that I want to use here. So first, let's load the libraries. And also, we create a client variable that gives us access to OpenAI, and then we can also interact with the OpenAI models. As you can see, I'm loading the OpenAI key from my .env file right here. Step number 2, we need a sample data. This is the Q&A pair. This is the cache data that we want to ideally store in a database and use it for searching the queries using a vector search to see if there is a close question to what the user is asking. So as an example, we have 5 questions along with their answers in our Q&A pairs. So we have how do I reset my password, what are the pricing plans, how do I create a new project, etc. So let's create our data. In the next step, we create the embedding for the cache questions. So as I mentioned, we want to keep it in a vector database. In this notebook, I'm not going to do that. I'm just going to create a variable and just keep everything in that variable. But let's also create the embeddings for our data. It's going to take a few seconds, and then it will show you that 5 embeddings were created. The embedding dimension is 1536, and this is a sample vector from our data. The models that you can use from OpenAI are these 3 models. As you can see right now, I'm using text embedding 3 small. This is the small version, like the small embedding model from OpenAI, the cheapest one, and it is actually very effective, so you can use it. If you want a more powerful model, you can go with text embedding 3 large. Next step is to define the similarity function. As I showed you in the presentation, to find the match for a query, we need to use cosine similarity. So this is how we can calculate the cosine similarity. We have 2 vectors. This is the embedding version of the user's question, and this is essentially the embedding version of each individual question inside our database, the one that we just created. Then we calculate the dot product, we normalize it, and we just calculate cosine similarity using this function right here. And to calculate the cosine similarity that we want to use for the project, we just need to use 1 minus the cosine similarity value. In that way, if the cosine similarity or if the cosine distance is equal to 0, it means that the questions are identical. If it is close to 0, it means that the questions are very similar. And if it is far, like 0.7, 0.8, that means that the questions are not related. So let's create the functions. Perfect. In the next step, we want to implement a cache lookup function. So this function gets the query, as you can see, convert the query into a vector. So this is how we can do it, query embedding, and then uses the vectorized version of that query against the database, the Q&A database that we just created, and compute the cosine distance for each one of those data. And eventually it gives us a list of those distances, and we can filter based on the threshold. So if the distance is less than 0.3, return that relevant question to me. So this is what this function does. Perfect. So we have the function ready. Step number 6, test cache hits. So up to this point, we created our semantic caching strategy. And from now on, we just want to play around with a few examples, see when we can get an identical cache hit result, when we can get close cache hits, and when we can get irrelevant cache hits, or the result is above our threshold, which means the query is not relevant to what we have in the database. So the first question is, how do I reset my password? This is the exact question that we have in our data. So we expect an exact match here. Perfect. Test 1, exact match. Cosine distance is 0, similarity is 100%. That is exactly what we expected. Question number 2, how do I change my password? This is the exact question as this one with just different wording. So let's try this one. Perfect. So we have how do I change my password as the query right here, and we have how do I reset my password in our database. So the distance is 0.1 or 0.15, and the similarity is 84.22%. So this is, again, a cache hit, and we successfully returned the relevant question from our database. The third question is how to make a new project. Perfect. So the distance is 0.08, which means we have a very similar question in our database. Similarity is 91%. And the question that was matched is how do I create a new project? In the next step, let's go through some questions that are completely different from what we have in our database. The first question is, what is the weather like today? So if we run this cell, we can see that we have a cache miss. The distance to the closest match is 0.88. Technically means there is not even a single question that is relevant to this one. And this is the closest match. What are the pricing plans? Totally irrelevant. And these are all the distances from our 5 examples. The next question is, what is the cost? So this question is a bit vague. you cannot really tell if it is the same as what are the pricing plans. So the best case scenario is actually when our system is able to consider it as a cache miss, and it asks the user follow-up questions. And in the next step, you can experiment with different thresholds. Let's test it together. So I have 0.1, 0.2, 0.3, up to 0.6 for the question, what is the cost? So as you can see, if we keep the threshold low, we are going to have cache miss for the question all the way down to 0.6. If we keep the threshold at 0.6, it is going to have a cache hit. It's going to match that question with this one, and it's going to return this question as the relevant question, which is really something that we don't want to see in our system. And finally, I prepared a cell for you that enables you to chat with this simple semantic caching strategy in an interactive mode. So you can ask different questions and you can see the result by yourself. You can change the threshold and you can play around with it. So that was a very simple way of implementing semantic caching. It is very similar to how you would implement a RAG pipeline, but this time you want to fine-tune it for identifying close or relevant questions to what the user is asking and return the answers when they are asking similar questions to what we have in the database. In the next notebook, I want to go through the comprehensive version of our notebook, and I want to show you, beside how we can implement semantic caching, how we can also implement different caching strategies such as exact match or fuzzy match, how we can implement re-ranking and add it to our strategy, and also how we can fine-tune it and how we can measure the thresholds to see what is the best match for our database. All right, so before we move on, I want to acknowledge a very fantastic course that I used partially in this project. So this notebook and the accompanying evaluation dashboard were inspired by the Semantic Caching for AI Agents short course by deeplearning.ai. I used several ideas and portions of their reference code alongside my own implementations. Full credit and thanks to the course creators for the foundational concepts and examples. All right, let's begin by loading the libraries for our notebook. As you can see here, I'm using sentence transformers. And the difference between this notebook and the previous one is that in the previous one, I was using OpenAI embedding models. In this notebook, I'm going to use some open source embedding models. So this will just give you flexibility to work with different models and see the difference. And we also have a few other libraries for implementing the strategies and also visualizing some graphs. First step, implement the data loader. What it does is that it looks at these two CSV files, FAQ seed and test dataset, and it's going to load both of them for us. So let's run this cell and let's see the result. So we have the data. Let's now load it and let's see what we have. So we have 8 FAQ inquiries and 80 test queries. So this is the cache database that we want to hold, and these are the test queries that we want to use to test our cache data. Let's also see the data that we have. This is our ground truth. These are the data that you want to collect for your business. For example, how do I get a refund along with its answer? And this is the test data. These are the data that may come from different users and what you need from this data. For some of them, you want it to actually hit the cache. And for that question, you need to get the answer directly from your cache database, from your cache data. And for some of them, you don't need that. So this is how we have cache hit label as true for some of the questions and false for the others. So the false here means that we don't want to actually get a cache hit for that question. So for this, you can either use an LLM to create these labels for you, or you can use a human for that. Of course, humans would be more accurate, but it's going to be a little bit more expensive and time-consuming. And we have source question ID here, which is 0, 1, 2, etc. And if I show you our cache data, you can see the ID column here. So we have 0, 1, up to 7. So what it shows is that what is the process for getting my money back? This question needs to hit the cache, and it's going to hit with, or it should hit with the question with ID equal to 0. So what is the process for getting my money back? Should hit with how do I get a refund? So this is how we can identify where our system is doing a good job versus where it's missing or it's hitting the wrong question. In the next step, we are going to load our embedding model. So for this notebook, I'm using all MPNet-based V2. This is another example that you can use, and you can see the dimensions here. So we have 768 dimension for the vector size or the vector length for this model, and we have 384 for this one. In the next step, we just want to test it. I want my money back. How do I get a refund? What is the weather today? So let's see what happens here. Vector shape, 768 for all of them, and this is the first 5 values in our vector. In the next step, we want to implement the vector search. So just like what we saw in the previous notebook, we are going to implement cosine distance. This time, we are also including 1 minus cosine similarity inside the same function. And I wanted to show you that cosine distance is not the only way that you can measure the distance between different vectors. There are other methods, but this is the most well-known strategy that you can use. But as an example, I also provided you with Euclidean distance, which is another technique that you can use for this purpose. So let's run this notebook. And now let's see how it works in practice. So we are comparing I want my money back with how do I get a refund. These two are very similar, right? Cosine distance is 0.33 and Euclidean distance is 0.81. You can immediately notice that the number changes. We had this example in the previous notebook as well, and it was a little bit closer. That is because OpenAI models are essentially more powerful, and they can give you a better result for these comparisons. And we are comparing I want my money back versus what is the weather today. So cosine distance is 0.94, it's very high, and Euclidean distance is 1.37, which is much higher than we saw here. So I don't recommend you to optimize on Euclidean distance, but I wanted to show you again a different method that you can implement here. In the next step, I want to show you different caching strategies. So we saw semantic caching in the previous notebook, but as I mentioned in the presentation, this is not the only caching strategy. And usually what you will implement in production is a layered strategy. For example, in the first layer, you might just go with exact match because there is no embedding model in place. It is very fast, and it is going to hit the exact questions that you have in the database. In the next step, you might want to implement a fuzzy match. So in case there is a small typo, this strategy is, again, much faster than semantic search, and it's still able to capture those scenarios. And finally, you may want to implement semantic search on the top and make it a very robust strategy. So let's create the code for all of this. So in exact match cache, I'm also normalizing my data. So if you see here, first I'm using lower method, which converts all the alphabets in the query and also in the questions in the cache data to lowercase. And also I'm using the strip method, which removes all the spaces, and it just gives us a raw string data to compare. So this single line is going to make this method much more powerful, because now this method is not case sensitive. That's the first thing. And also it's not sensitive to extra spaces. So if I have a question like, how do I get a refund? And also the user asks, how do I get a refund space? And then the user adds the question mark. It is not going to matter at all, and it's going to still be caught with this method. Okay, so let's run this. And in the next step, we want to implement fuzzy match. So for this, as I mentioned in the presentation, we are going to use a technique or a method called Levenstein distance. It's a very simple and effective method to have alongside your semantic caching. In the next step, we have semantic caching. This is exactly the same method that we saw in the previous notebook. This time, the code looks a little bit different. It is coming from that online course, but essentially the functionality is the same. So let's also run this cell, and let's instantiate all our classes and save them into a variable. So we have exact cache, fuzzy cache, and semantic cache. So perfect. In the next step, we are going to just run a quick example. Let's run it and let's see what happens. Okay, so I have a couple of questions, and I want to show you the difference between those strategies. The first question is, how do I get a refund? This is exactly similar to one of our questions in our database. So as you can see, we are going to get a cache hit in all these methods. Next, we are just going to change capital I to lowercase I. And I wanted to show you that this change should not affect any of our methods. And as you can see, all of them were successfully captured that question, and we got a cache hit with all of that. Especially this one was for testing the exact match because of that single line that we added to normalize the question. Next, we have how do I get a refund, but this time we have a typo in it. So this time, as you can see, exact match is going to miss, but fuzzy match is going to successfully give us a cache hit. So this is the power of fuzzy match. Again, semantic caching is going to work with all of those scenarios. I want my money back. This time we have a question that is worded differently, but we have a close question for this one in our database. So both these methods are going to fail, but semantic caching will be able to capture that one as well. Refund, please. Again, we are going to get a cache hit with semantic caching. And finally, what is the weather today? We are going to have a cache miss in all of that. So this is the difference between these three methods. And that is why I mentioned that essentially what you want to have in your project is a combination of these methods that suits your data the most. And we are going to see the response time of these methods in a second too. So in the next step, I added a few different functions that shows you how fuzzy search works. I'm going to skip them, but feel free, of course, to try that and to play around with these thresholds and see the differences. In the next step, we get to the evaluation part. So first, we are going to see the performance comparison, time versus accuracy. Then we are going to see the confusion matrix analysis. And finally, we will see a detailed cache evaluation. This is the main concept behind the dashboard that I created for you. So in the first cell, we are going to run our test questions against our cache database, and we are going to see the time difference for each one of the methods. So with exact match, our hit rate was 0%. And on average, it takes 0 milliseconds to run each one of our queries against our cache database and see if there is a hit. Just to remind you, we have 8 questions in our cache database and we have 80 test questions. So this is the average time to run each query on the database. With fuzzy match, we got 13.8% hit rate. The average time was 0.4 millisecond and the total time was 33 milliseconds. And for semantic caching, we got 32.5% hit rate. We have 9.99 millisecond average time, and we have near 800 millisecond for the whole database. With exact match, we had the fastest performance, but it had the lowest hit rate. With fuzzy match, we could catch typos. It was a little bit slower than exact match, but it is still much faster than semantic caching. But with semantic caching, we had the highest hit rate, and of course, the trade-off is the speed here. So in the next step, we want to plot the confusion matrix. Just to note one important factor, if you start to play around with the threshold that we defined earlier when we created the instances from exact match, fuzzy match, and semantic caching, you will get different results. So keep that in mind, that if you start to play around with the threshold, the result will change. And that is the whole point of fine-tuning this strategy. The next step is to plot the confusion matrix for the current setting, for the current threshold, and on each one of our methods. So let's do that. Here, I have 3 confusion matrices, one for each technique. So with exact match, we have accuracy equal to 70%, precision equal to 0, recall 0, and F1 score is equal to 0%. So the reason that we have accuracy equal to 70% is that, let me show you the data set again. So here, this is our test data. Exact match returned 0 cache result for our test data, meaning for all these questions that you see here, there was no cache hit. So if we do that and if we just return no cache hit at all, technically speaking, for these type of questions that have cache hit equal to false, the strategy is doing the wrong thing by not providing a cache hit. So that is why we don't optimize on accuracy and we optimize on recall and precision. Because even if your system is biased to one direction, either it is returning a cache hit for all the questions, or it is not returning a cache hit for any of the questions. Accuracy is going to be somewhere between 0 to 100, and that is not reliable. But with precision and recall, we can optimize the system and we can get a very good performance. Okay, so let's go back. I missed it. Perfect. So with fuzzy match, we have the accuracy equal to 68.75, precision 45%, recall 20%, and F1 score 28%. So you can see that with utilizing fuzzy match, our system is already doing a much better work. And finally, with semantic caching, accuracy is equal to 87.5%, precision is 76.9%, recall is 83%, and F1 score is 80%. That is a much, much superior performance compared to these two methods. Okay, you can also go through the details here. This just provides you with some extra information, such as the number of true positives, true negatives, false positives, and false negatives. And if you want to optimize these strategies on your data, this is a very important thing to take into account. So essentially, you have to go through your questions, check false positives and false negatives, and understand why it is happening. And then try to find the threshold that first suits your data the most, like it is giving you the best performance, and also adjust the data if necessary. And that is exactly the purpose behind the next couple of cells. So I added these cells later on when I was working on the notebook. That is why you see I load the data again here. You have a few classes and functions that allow you to dig deeper into your questions and find out about true positives, see the false positives, false negatives, etc. So the most important part is to go through these two classes, identify the root causes and find out why you are getting false positives and false negatives, and try to find solutions to address these two scenarios. Beside that, true positives and true negatives are the things that your system is successfully caching with every question. All right, so up to this point, we saw how we can implement different caching strategies, including semantic caching, and also we saw how we can evaluate the performance of our system. In the next step, I want to show you how we can optimize our caching strategy. And the first thing that you want to optimize for is, of course, the threshold. One easy way to do that is to create a list of reasonable thresholds and to run the test for each one of them. So I start with something as low as 0.1, and here I went to 0.5. But for example, if you're working in a sensitive domain like healthcare, 0.5 probably doesn't make sense for you, and you want to stay within this range. So it is very important that these numbers should first make sense, and also give it a try and see how it works for your system. So let's run this cell. As you can see, for each threshold, I'm getting the precision, recall, and F1 score. So we are running the test for all these thresholds, and we can get the best F1 score. So here, I want to optimize for F1 score. But as I mentioned in the presentation, especially when we get to the re-ranking, one good way to think about this optimization strategy is to optimize for recall if you want to add re-ranking to your system. So with the threshold of 0.45, we got the best F1 score here. The precision is 0.75, recall is 0.91, which is very high. Accuracy is 0.88, but really it doesn't matter for us. But F1 score is 0.82. So it gives us a hit rate of 0.35. So if I use this setting right now in my production, based on the test data that I have, 35% of my questions, the user queries, would hit the cache database, which is going to essentially reduce cost and make the system much faster. Let's also visualize this test. Okay, so as you can see here, I have three different graphs here. The most important one is this one on the left. This one shows exactly what we saw on the top in the table, but in the form of a graph. And this is where the best F1 score happened in our test case. As you can see, this is the recall of 0.91, precision of 0.75, and F1 score was around 80. What was the number exactly? So it was 88%. So following up what I just explained earlier, for example, if I want to add a re-ranking method to my caching strategy, I probably would even go a little bit further, and I may choose 0.5, because what I want to do in that case is to return a couple of relevant responses and then pass them to a re-ranker model. But if I don't want to use that, I would definitely optimize for F1 score, and I would use this setting right here. The next thing that you want to test is the embedding model. And by the way, I didn't explain these two models because this is just the precision recall curve, and this one, as I mentioned, is the most important graph. And I just wanted to show you what happens if you plot hit rate and accuracy versus threshold. Just imagine that if you optimize for accuracy, you're going to get the threshold of probably 0.3 right here, because for this, we got the highest accuracy. And that is clearly not a good threshold. I would recommend you to also use different embedding models, especially if you want to use open source models. If you want to use a model from, for example, OpenAI, the choices are limited, and you can easily run like 2 or 3 different models and test with each one of them, and eventually choose the one that has the highest accuracy and also the cost has a reasonable cost for you. But in case you want to go with open source models, I would definitely recommend you to go and test different models and see which one would suit you the most. So here I have 2 models. One of them is this one from MiniLM, and the other one is MPNet. And I just want to see the performance difference here. So if I run the cell, you can see that the F1 score for MiniLM is 70%, and the F1 score for MPNet is 82%, and that is a huge jump. So definitely this model is the better one, but of course, it's a little bit heavier. And by heavier, I mean it requires a little bit more computational power. But looking at the time, ironically, I saw that the performance, the average time for MPNet was also lower than the average time for MiniLM. So that's a little bit surprising to me, but it depends on so many different factors. So this is actually great that you can see testing these models may even surprise you. But usually, if you're using a larger model, you expect a higher average time for running each example. Anyway, this is an interesting case. We got the better performance, and also we got a faster result. In the next step, I want to show you that even if we choose the best F1 score for our system, that does not mean that our system is not going to make a mistake. So let's run this cell. So what this cell is doing is that it is just going through the examples, checking them, and finding the false positives and false negatives. So the evaluation step doesn't end at finding the best F1 score. After that, as I mentioned, you have to go through false positives, false negatives, and see as the system owner whether you would tolerate these type of mistakes. If you want, you have to go back and do the optimization again. You may decide to lower the threshold and make the system more strict, or if you have more room and more flexibility, you can increase the threshold and have a higher hit rate. So this is a loop at the end, and you have to go through it again and again until you find a sweet spot for your system. All right, in the next step, I want to show you how we can add re-ranking. And what I want to cover in this section is first the re-ranking strategies, which are simple keyword re-ranker, cross-encoder, and LLM re-ranker. And we'll also go through the evaluation phases. And again, just like what we saw in the previous sections, we are going to see the difference between speed, accuracy, and cost. Just a quick note, for this section, I'm not going to use the thresholds that we saw in the previous section. And I will not also optimize the re-ranking strategies, because I want to show you what will happen if you just add a re-ranker to your system without going through the optimization steps. So let's start by running this cell. This class allows me to perform essentially what I need for my re-ranking. It gets the top K candidates by embedding similarity. I'm talking about this method, of course, and it re-ranks candidates using re-ranker function. So in the next step, we want to go through different re-ranking functions. So first, simple keyword re-ranker. As the name suggests, this method re-ranks the candidates with keyword overlap, and I wouldn't recommend you to use it in production. Definitely go with a cross-encoder or an LLM if you want to add a re-ranker. So the way that it works is that it gets the query, it normalizes it, then we go through each one of our candidates, and these are coming from our cache sheet from the database. Then we normalize each candidate, we compute the overlap, and using this formula here, we compute a score and we assign it to that candidate. So let me show you how this works here. So I have two demo queries. One is I need my money back, please. The second one is how do I get a refund for my order? So if I look at my database, I have this match here. How do I get a refund? The first one, we are going to have a match because of the embedding distance, but the re-ranking score is a little bit low because there is no overlap among the words in these two. But if you check this one, how do I get a refund for my order versus how do I get a refund, now the re-ranking score is going to be much higher because we have a couple of words that are identical in these two. So this is how this method works. Next, let me create the cross-encoder re-ranker. And for that, I'm going to use the transformers library. And this is the model that I want to use for the cross-encoder. All right, so we load the tokenizer, we load the model, and this is what we are going to use in our class. And this is the main method that gives us the prediction, which is essentially the score that we are getting from the model. This model is trained to receive an input for the query and also an input for the context and make a prediction that shows how close those two are with each other. So this is the prediction method, and this is the class in which we are going to execute that. So as you can see, it gives us a score, and we are going to store everything to both show it to the user and also use it in the comparison. So we have the re-ranker type, re-ranker score, and the re-ranker distance, which is 1 minus our score. Perfect. Let's create the cross-encoder, and let's see a few predictions from it. So we have what is the capital of China, which is going to go against this one, Beijing. And we are going to use how to implement quicksort in Python. Same query against both the second and third answer. So the second one is introduction of quicksort, and the third one is the weather is nice today. So as you can see, the first one gives us a high score because capital of China is Beijing. Introduction of quicksort is very relevant to how to implement quicksort in Python. It is not the answer, but it just checks the relevancy. Keep that in mind. So it gives us a very high score for that. And finally, for the third one, we are going to get a very low score. And that means that these two are not relevant at all. So that is how a cross-encoder works. Okay, so in the next step, we want to create our LLM reranker. So for that, I'm going to use OpenAI GPT-4o Mini. So here I'm loading my OpenAI API key, and you also need to have it in case you want to run this part of the project. So let's just create the classes and the functions that we need for it. We have the similarity result class that forces the model to give us a reason and also the comparison result. So for the reason, it's going to explain why the answer was true or false. And true means that the sentences meant the same, and false means that they were different. And by sentences here, I mean the query and the context. Okay, so we have some other classes just for creating the LLM reranker, and we have the prompt here. This is super important. So if you want to optimize the LLM reranker, one of the most important steps is to optimize the prompt. If you want to have a good performance from the large language model, this is the most important thing that you can work with. And beside that, of course, the model that you choose. So I'm now using GPT-4o Mini, but you can also use more powerful models. So let's run this cell, and let me also show you how we are going to return the results. So this is the reranker type, which is LLM. Reranker score is 1 if they are similar, and it is 0 if they are not similar. And the reranker distance is, of course, 1 minus the reranker score. So it is 0 for similar and 1 otherwise. And in the next few cells, I'm just going to prepare some functions that are helping me to run the comparison. You really don't need to understand any of these sections because these are just mainly for this notebook and to allow us run the test here. So let me initialize the rerankers, and let me, okay, so we have the rerankers ready. So the baseline cache with no reranking is what I'm going to use as the baseline. Simple word rerank cache is our first strategy, cross-encoder is our second strategy, and finally, we are going to also use the LLM as the reranker. So let's evaluate the performance of our system. So in this cell, we want to wrap up everything, and we want to go through each one of the questions in our test case. We are going to check the cache database and return the most relevant questions to that. And we are going to return the query with each one of the returned questions to our reranker. And we ask the reranker to choose the most relevant question. And we compute how accurate each one of the rerankers are. So let me first run this cell because it's going to take some time, especially for the cross-encoder and the LLM as the reranker. And let me just show you what we are doing here. So we are using this class, which is already instantiated with distance threshold of 0.36. So this is not the optimal threshold that we found together in the evaluation part. Okay, let me go back. It is still running, and that is expected. So cross-encoder is already done. We are going through the large language model, GPT-4o Mini. I'm not going to pause the video or skip this part of the video because I want you to see the time difference between GPT-4o Mini and and the other methods that we have in our rerankers. So as you can see, this is much more time consuming than even the cross-encoder. And that is something that you have to take into account when you want to design your system. Perfect. So the evaluation is complete. Let's print out everything in a nice format here. So for the baseline, no reranker at all. Precision was 90%. Recall was 75%. F1 score was 81.8%. And the average time was 0.88. With single keyword strategy for reranking, precision was 53.8%. Recall was 100%. And the average time was 0.67. The cross-encoder here, the precision is 52, recall is 100%, F1 score is 68, and the time is 5.54. And for GPT-4o Mini, precision is 100%, recall is 54, and the F1 score is 70%. And the time is 61. And the most important factor that you have already noticed is the reduction in F1 score. This is what I wanted to show you. So by adding the reranker to the system and not optimizing it properly, not only I did not help the system to become better, but on the other side, the performance downgraded. This is what I've seen a few times in production grade projects, and this is what I wanted to show you. So many people might think that adding reranker by nature, it's going to make the system perform better. But that is not the case. It is very important to optimize the system and to make sure that each component that you are adding to it adds real value. All right, let's also visualize the performance. I'm not going to go through the details because we have already covered it, but I just want to show you how you can also visualize the performance of the rerankers, compare them, find the false positives, find the false negatives, and also optimize in that regard. So let's see some of these images. I'm passing through them because in the dashboard that I prepared for you, I have already covered everything. This is also just a quick wrap-up in case you go through the notebook. So by this point, I expect you to have a very good understanding of how semantic caching works, how you can add reranking models, and how you can optimize this to improve the performance of your systems. In the final part of the video, I want to show you how I would utilize this technique and how I would add it to my own projects. So the first thing is, of course, to have a playground, some sort of a dashboard that allows me to run tests on my data. And for that, I have already prepared evaluation dashboard for you. I'm not going to go through the backend because backend is essentially coming from everything that we saw in the notebooks. And I just created a Streamlit app for it just to make it more beautiful and also allow you to interact with it in an easier way. So to run the dashboard, all you need to do is to go into evaluation dashboard in case you haven't done it already, but you have an environment ready and that environment already contains all the necessary libraries. Run this command. So let me just bring it here. So pip install -e dot, it's going to just create a package for you. It is going to take a couple of seconds, but that should be quick. Perfect. Then we can run Streamlit, run, app.py. So that's all it takes to run the app. It opens this page for you, and then you can start using the dashboard. So this dashboard is designed to give you everything that we have seen so far and even more in an automated format. So in the landing page, we just have a general description of what the dashboard is, how it works, and what you can do with it. Then we have the About page that is a short summary of semantic caching, re-ranking, and everything that we have covered in the video so far. So this is just here for you in case you want to refresh your memory and go through some details again. Then we have the data page that allows you to load your data. So first, let me walk you through the data structure. There are two CSV files that this dashboard expects. The first one is groundtruth.csv. The second one is test dataset. These are the columns that you need to have in groundtruth.csv, and these are the columns that you need to have in this test data. The purpose here is this is your cache content, the questions and answers that will be stored in the cache, and this is the data that contains the test queries that represents your real business needs, and it should include variation of cached questions, unrelated questions, and edge cases and paraphrases. So this is just a reminder on what needs to be included in your data. So I already included two sample data for you, and this is the data that I was using in notebooks. But you can also load your own data. And for this test, I want to load a new set of data. So first, let's load the ground truth, and then let's load the test data. Perfect. So load uploaded data. This is just a high-level summary of what we just uploaded. We have 15 ground truth entries, 42 test queries, and it shows that 27 questions in our test dataset, or 64.3% should hit cache, and 15 of them should miss cache. This is the ground truth dataset. We have ID, question, and answer columns, and this is the test dataset. We have question, answer, source question ID, and cache hit. So this is exactly similar to what we use in our notebooks. We have distribution analysis that shows the expected cache behavior and the test query distribution. It also gives you some advice or some tips on what is a good range for the distribution. We have text analytics. In case the number of characters in your question is an important factor, this shows you that, and this shows you the distribution, so you can make sure that your dataset meets the requirements. And we have data insights that gives you some insights about the dataset. For example, in the data that I uploaded, we have adequate ground truth size, we have a small test set, we have a well-balanced dataset, we have low test coverage. Test to ground truth ratio is 2.8, which is a little bit low. So aim for at least 5:1 for robust testing. And we have consistent question length. So these are the important factors for me. So, and of course, in case you need other factors to be taken into account, you can adjust the dashboard and you can modify it. Okay, next we have the testing phase. This is where you can test different caching strategies. You can choose between exact match, fuzzy match, and semantic cache for your comparison. You can play around with the threshold for fuzzy distance. You can choose the embedding model of your choice. You can play around also with the threshold for semantic distance. I will talk about these top K results in a moment. And you can also choose the number of queries that you want to take into account. So I have 42 test questions. And here, if I just want to run a quick test, I can include less test queries here. So let's just choose 20. Let's choose all the methods, and let's run a quick test. This is just also a preview of our test data. This is random. So let's run the test. Perfect. So this is the test result. And for each query, we get the expected, the exact, fuzzy, semantic, and the distance. So the distance shows the actual distance between this query and the most relevant question in our cache database. And these are the result of each individual method. And if you start to play around with the threshold, this should change. So for example, if I increase fuzzy threshold to maximum and reduce semantic distance threshold to minimum, I should expect this to change. So let's see it. Perfect. So as you can see, fuzzy match is just giving a hit for every single query, and semantic caching just failed for all of them. So you can play around with different thresholds and you can find a sweet spot here. So let's put it back to 0.4 and also 0.4 for this one. Let's run the query. Okay, so this is the test result. You can also get the distribution between the distance, mean, standard deviation, etc. This gives you just a good understanding of what is happening inside that test. And also you have query level inspection. So for each individual query, you can choose that query and you can see the top 5 relevant questions in your cache data. And this is exactly related to this one. So if you change the number here, you will see more or less number of questions from your cache data. And you can see the distance, you can see the status, and you can eventually understand how each query is matched with a question in the database, and you can debug and go deeper if you need to. This is the top matches distance decay, so this is exactly what we saw here. We have a strategic comparison, expected, exact, fuzzy, and for each one of them we have hit rate, accuracy, and average distance here. We have we have the average time and total time for each individual method, and also the confusion matrices and F1 score recall precision along with true positive, true negative, false positive, and false negative. So essentially, this page gives you everything that we covered in the tutorials, and this is a great tool for better understanding what is happening inside the dataset. Perfect. So let's go to the next page, which is the optimization page. So this is where we are going to actually optimize those methods for our dataset. So just like what we saw in the notebook, we are going to create a list of thresholds. So this is the minimum threshold, the maximum threshold, and the step size. So let's just reduce it to 0.4, maybe increase it a little bit to 0.1. You can choose different embedding models, and as you can see, you have 4 options here. So let's just keep it as it is, and then you can run the optimization. So let's run it. So it's testing the first model, which is mini-LM, and now it's testing the second model. Perfect. So this is the result. So for each individual model, you can see the performance here. So if I change the model, everything will change in this page. So best F1 score for mini-LM was 85.71%, best precision was 100, and best recall was 84%. This is the exact same graph that we saw in the notebook, and it shows the best F1 score for our test dataset. And precision recall curve, hit rate and accuracy versus threshold, and some recommendations here. So this page also gives you some advice based on the result, and you can see also the detailed result right here. So let me go up. Let's go to model comparison. So you can see the model comparison between the 2 models that we chose here. And if you start play around with the threshold here, you can see that it changes live, and it shows you how those models would do with different threshold on your data set. So this is a very handy tool, and it can quickly give you a good sense of what is the best model for your use case. Optimal configuration, this just shows you how you can implement the strategy for your use case in code, and detailed metrics. Again, this gives you all the details that we have seen together: threshold, precision, recall, F1, accuracy, and hit rate for each individual model. So this just allows you to quickly run tests for your test data and find out that the best F1, the best recall, or the best precision based on what you're looking for your dataset. Next, we have the re-ranking page. So as you can imagine, you can choose all the different methods that we saw in the notebook together, based on simple keyword re-ranker cross-encoder and GPT for Om-Mini. So for this one, you need to have your API key, as I explained, in the .env file, otherwise it wouldn't work. So for now, I'm not going to select it because, as you saw in the notebook, it's going to take a very long time. So you can choose the embedding model. You can choose the threshold for your base cache, and you can also choose, again, the top candidates. So this one is As I explained, when you add re-ranking, instead of just returning the most relevant query, you would return the top 5 or the top, depending on the value of k, the top k relevant queries from your cache database. And then you pass all those queries to your cross-encoder or to your LLM reranker. So this is the number that would allow you to increase or reduce the number of returned queries from the cache data. And for the cross-encoder model, I also provided you with a few options here. You can choose different models and you can see which one would suit you the most. And this is the cross-encoder threshold. You can also play around with this, and this would give you a sense of like the best threshold for your cross-encoder. So with that, okay, so let's just keep it as it is. Let's just run the re-ranker comparison. So it's now going through each re-ranker one by one. So I chose, I will always keep the baseline because that just gives me a good sense of whether the re-ranking strategy that I'm adding to my system is actually helping or not. Simple keyword re-ranker, you can safely remove it. That is really not very beneficial. And cross-encoder is probably the safest bet and my first choice if I want to test something. So I have the metrics here: precision, recall, F1 score, accuracy, hit rate, and time, the average time for each re-ranker. The best performers, as we saw in the notebook, if we don't optimize, most probably we are going to get the baseline as the best performance. Best recall, for this case, was the cross-encoder with 95.7%. Best F1 score was the baseline, and the fastest was simple key re-ranker. So detailed breakdown for each one is right here. You can expand them, you can explore them. We have the confusion matrices for all of the methods that we chose here. We have the performance chart that, for example, here, it shows the classification metrics comparison, precision, recall, F1 score, and accuracy, and processing time comparison. So it shows like which method was fastest versus which one took the longest. And as you can imagine, cross-encoder, of course, would take the longest among these three methods. So here, simple keyword re-ranker was almost identical to baseline with less than 0.01 second. So my assumption is that that was just probably a miscalculation and they were technically the same. Otherwise, I wouldn't expect baseline to be 0.01 second slower than this one. Most probably they should be the same. And speed versus accuracy for different methods, you can see that again in this graph. And finally, the recommendations. All right, so that was it for the dashboard. For the next step, I want to show you the RAG chatbot with semantic caching. So this is, as I explained in the presentation, a RAG chatbot from LangChain that I took and I just added semantic caching to it. There is no re-ranking involved. It just has semantic caching added to it. So now let's run our RAG chatbot. So I will go to that folder, Streamlit run ragapp.py. It is going to open a Streamlit app just like the previous one, but this one is going to be a chatbot. The landing page shows us some of the questions that we can ask from the database that I've already created for this chatbot. And in case you use a different database, these questions would not change. So the landing page is kind of static. You have to either ignore it or you need to just adjust it for your use case. Let's initialize the assistant here. So it's going to load the vector database, load the collection, and we have 36 documents, and Taskflow Assistant is ready. Perfect. So now I can start asking questions and interact with our chatbot. For this part, I prepared 4 questions, and these are the questions that I want to ask from our chatbot. 2 of them, I already have them in my cache data, and 2 of them, I don't have them there. Let me also show you the cache data. So this is the cache database that I already have for that chatbot. And this is, in general, the documents that I have for, let's say, my company. So let's test those 4 questions and let's see what happens. The first question is, I want to create a new project. So my expectation is an instant hit. Perfect. So answer from cache, similarity score was 93.82%. And this is the answer. And if I show you that question from cache, this is the first question. How do I create a new project? And I just asked, I want to create a new project. So technically, they are the same. Next question is there a way to export the data? As you can see, it's immediate. So it hits the cache and it gives you the answer. Let's also double check here. So for that, can I export my data? This is the target question. So that's how fast it is. Now let's ask a question that I know it's going to hit the RAG flow. So can I automate repetitive workflows? The answer should be in my documents. So it went into the thinking mode. It means that it activated the RAG pipeline. So there you go. If it allows me, I can scroll up. Perfect. So can I automate repetitive workflows? Yes, you can automate it with the full answer. One important factor when you implement a caching pipeline is to constantly update the database. And I talked about it in the presentation. You need to remove the old queries that do not have valid answers anymore. And you need to also add new queries in case they are coming up a lot. So one just simple way that I implemented in the chatbot is just simply to ask the user. So was this answer helpful or not? If I hit yes, add to cache, it is going to add it to my cache database. And if I hit no, don't cache it, it is just going to ignore the answer and it's going to move on. And as you can see on the left, I also have a quick summary of what is happening in this chat session. So far, I asked 3 queries. My hit rate was 66.7%. I had cache hits for 2 of them. And so far, the user didn't approve anything. So let's approve it. And perfect. So it was added to our cache data. And let's also verify that. So this is my actual cache data, but since I wanted to keep it static so I can show it to you in the video, I pointed to task flow cache approved. So in case in the chat session you approve something, it is going to create this new CSV file for you, and it's going to add those approved questions to this file. So the last question is, can I automate repetitive workflows, which is the question that the user asked, or I asked earlier, and this is the answer, and it was approved for our use case. So that is perfect. So now let's also ask the final question. Can I filter tasks by multiple criteria? Again, it activated the RAG pipeline and it went into the thinking method, and this is the answer. Yes, you can filter tasks by multiple criteria. So the answer was indeed in our documents, and it is again asking the question. As you can see, the hit rate went down to 50% because 2 out of 4 questions hit the cache and 2 didn't. So let's also add this one to our cache data. Perfect. Let's go back. This is our last question. Can I filter tasks by multiple criteria? So this is one way to do it, but you can also implement a more automated pipeline to verify the answers and add them automatically or ignore them automatically in case you don't want direct human intervention in your database. So that is another aspect. I didn't cover it in this video, but that by itself is a different thing that you may want to add to your system. And I also forgot to mention that you can play around with the threshold in this chat session, and you can test different cache similarity thresholds to see how the RAG chatbot's behavior would change. So that's semantic caching. If you have any questions or if you implement this in your projects, let me know in the comment section. I read all of them and I'd love to hear what you're building. Everything that we saw in the video is in the GitHub repo, and I'll add the link below. And also, if you find this helpful and like more deep dives like this, hit that like button and subscribe. And that was it from me. Thank you very much for watching, and I'll see you in the next one.